Greetings, mathophiles. Welcome to a video in which we take a look at a bit of a twist that you might encounter in situations where you're asked to differentiate a function defined as an integral. This is essentially an extension and combination of the chain rule and part two of the fundamental theorem. I'm going to assume that you're familiar with using the chain rule as a differentiation technique. And if you need some background or some refreshment on part two of the fundamental theorem of calculus, I'll put a link to a video in the description for this video. But just for convenience, I'll also flash right now on the screen the statement of the fundamental theorem part two, which says if some function f is continuous on some interval I and some number a belongs to that interval, then the derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. And so this is basically one of the angles on the notion that differentiation and integration are inverse processes to one another. There's some qualification, there's some technical detail, but in essence we're saying that differentiation undoes integration. Before we forge ahead with an example that combines both the fundamental theorem and the chain rule, let's do just a fundamental theorem part two example to sort of get our juices flowing and give us an opportunity to address maybe some issues of domain. So I'm going to ask, what is the derivative of the function defined in this way? Integral from 2 to x of square root of t plus 4 all over the natural log of t dt. Fundamental theorem part two says that this is just the square root of x plus 4 all over the natural log of x. But we need to be attentive to issues of domain because this is only going to be good for x's that are on some continuous interval containing 2 that can be inserted into this integrand. So we need, for example, x to be greater than or equal to -4. And for the natural log to be continuous, we need x to be either between 0 and 1, or we need x to be greater than 1. Now, x greater than or equal to 4 contains 2, no problem there. And in fact, both of these are contained within x greater than or equal to 4, so that's not really going to be a constraint on us. Now, which of these is it going to be? Well, we're integrating from 2 to x. And if we try to integrate from an x between 0 and 1 to 2, it's not going to work because we're going to have to cross a discontinuity. So the domain over which this relationship holds is x greater than 1. Now let's go ahead and get a little fancier. Let's ask the question, what is the derivative with respect to x of the integral from 2 to x squared of, just for laughs, let's keep it the same, t plus 4 square root all over ln t dt? Well, it's maybe not obvious what to do, but wherever this integrand is continuous, it has an antiderivative according to the fundamental theorem part two. So let's say that the antiderivative of this integrand is some function big F. Then by fundamental theorem part one, this is going to be the derivative with respect to x of big F of x squared minus big F of a. Let's see what we can do with that. Derivative of big F of x squared according to the chain rule, that's where it comes in. According to the chain rule is big F prime of x squared times the derivative of x squared, which is 2x. F of a is a constant. I don't know what it is, but it doesn't much matter to me. Its derivative is 0, and just for the record, I will make that notation. So now what is f prime of x squared? Well, it's whatever I get when I stick x squared into the integrand, because the integrand is big F prime, right? So this should be square root of x squared plus 4 over the natural log of x squared times 2x. And then we have to, again, think in terms of domain. So we need, basically here, we need x squared to satisfy whatever x had to satisfy over here. And so it is going to be the case that x squared's got to be greater than 1, which means either x is greater than 1 or x is less than -1. But if x is less than -1, that sort of takes us across a discontinuity, and that's not going to be any good. So there's our first example, sort of the long way around, of differentiating a function defined by an integral where one of the limits of integration is itself a function. Let's take a look at a more generically set up version of this question. Let's ask ourselves, what is the derivative with respect to x of the function defined by the integral from a to g of x of f of t dt? And let's assume f is continuous, let's assume g is differentiable, let's assume all the things that might be necessary for us to assume, and we'll clean that up a little bit later in the video. So if little f is continuous, by the fundamental theorem part 2, it has an antiderivative. So let's call that antiderivative big F. And then this thing is equivalent to the derivative with respect to x of big F of g of x minus big F of a. But if I differentiate big F of g of x, I get big F prime of g of x times g prime of x, straight up chain rule. And f of a being a constant, its derivative is 0. But now big F prime is, of course, little f. So this is little f of g times g prime of x. And what you get at the end of this process is the notion that in a situation of this type, I just take the integrand, plug in this function that is the upper limit of integration, and then multiply by the derivative of that function. So you don't have to take the long way around and be writing these big F's all the time. You can just sort of recognize the relationship and then cut to the chase. I'll place on the screen a more formalized version of this. And what it says is that the derivative of the integral from a to g of f of t dt is equal to f of g of x times g prime of x, given the right conditions. And the right conditions are that f has got to be continuous on some interval containing I, and that g has got to be differentiable, and this will then be true for all g of x's in I, all x's for which g of x is in I. We could really go nuts and ask ourselves what happens if we have a situation in which the lower limit of integration is also a function. It shouldn't be too big a leap to imagine that the lower limit would play out in a manner similar to the upper limit, except because of the order of the subtraction in the fundamental theorem part 1, you would just get a subtraction of another term that was analogous to the one that we saw initially with the upper limit. Let's close off with one more example, and then we'll call it good. Let's ask the question, what is the derivative with respect to x of the integral from 0 to the sine of x of the square root of 1 minus t squared dt? Well, what we've just discussed would lead us to go immediately to the idea that this would be equal to the square root of 1 minus the sine of x squared. It's not how we usually write it, but I want to really emphasize the composition that's going on, times the derivative of the sine of x. Now, the square root of 1 minus the sine squared, of course, is either the cosine or the op cosine according, so one could do some simplification here if one was willing to pay the price of discussing that plus or minus. But let's definitely talk about domain. It needs to be the case that any x's for which this relationship is true satisfy some things. And so first, let's ask ourselves, what are the things that we can plug into that square root down there? Well, 1 minus t squared has got to be positive, which means t has got to be on closed -1 to 1. And then we've got to ask ourselves, what kinds of x's produce signs that are on closed -1 to 1? And the answer, fortunately, is all of them. We need sine of x to be on closed -1, 1, but sine of x is always on closed -1, 1. So there's not, in this case, there's not really cause for worry. Whereas in other examples that you may encounter going forward, that might not be as true. So you need to be attentive to issues of domain. I hope this quick introduction to fundamental theorem meets chain rule has been helpful to you, and that you're now in a position to pull it out in situations where it would be a time saver for you. So enjoy it. Happy mathing.